Okay, we're moving on to transition curve now. Okay. Now, before we go on further, let's look at the title is a transition curve. Transition means changing, okay, from one to another, from one condition to another condition. In this case, what should I say? One situation to another situation. So it's a curve that allows something to change. Okay, so for the time being, just put in your frame of mind that this is a curve. Something changes when you go through the curve. Okay, let's see what it does. Okay, looking at the forces acting on the vehicle. So when you're entering let's say you are in a car or any vehicle. So when you're driving on a straight road comfortably, then suddenly you'll be negotiating, you'll be taking a bend. Let's say now you're taking a bend, a corner to the right. So what would you feel inside if the first thing of the car is to slow down, or the vehicle to slow down? Even after slowing down, you feel that as the vehicle taking the corner, you feel that your body will be leaning away from the center of the curve. You feel like you will be thrown out from the car. Okay, so that force, that lateral force acting on you, or that you're experiencing, will be greater if the vehicle hasn't slowed down. Okay, so that force is what we call as the centrifugal force. Okay, so when we talk about transition curve, we are talking in the terms of this force. Okay, what we're trying to do here, we're trying to minimize, okay, the force acting on the passenger or the driver whenever the vehicle is taking a curve or taking a corner. Okay, I've got a simple sort of illustration here. That car, okay, if you look at the car, level, let's say for now it's a level road, okay, a level road like that. On the road surface, we're going to take, we are not going to go into detail by taking the force of friction on the tires and so on. So we just take simple terms. Okay, if W is the weight of the car, okay, so when this car goes through this bend here like that, there's a force, okay, pushing or making the car tilted like that. So that force is what we call the centrifugal force. So obviously the occupant in there will feel that you will be like feeling like you will be thrown out from the car. Okay. Now that force there, P, the centrifugal force, is given by the equation there, which is proportional to the vehicle speed and inversely proportional to the radius. So the smaller the radius, obviously, the value of P will be greater. So that's the basic reason why if the corner is sharp, you have to really slow down. If you don't, the car might overturn, and so on. Okay, so that's talking about the forces or the force acting upon you when you are taking a road curve. So when we talk about transition curve, this is what we're dealing with, and we're gonna try to minimize, okay, the value of P. We cannot say at this point in time, we cannot say to try to eliminate altogether, but at this point in time, we're going to say that is, for now, it's going to be like to minimize. Okay, looking at this figure here, when you traveling on a straight line, on the straight road, okay, the radius of a straight line is obviously infinity, meaning that P is 0, centrifugal force will be 0. But as soon as you hit immediately you lift the tangent point onto the circular curve drawn, denoted by the red arc here, you will have a value. Okay, you will have a certain value. That value there. Okay. For argument's sake, I'm just going to give a number. It might not be correct. I'm just going to give a number. Let's say that's 50. Okay. So what you have now, you have 0 here, and immediately after the tangent point, you have 50. Okay, so there'll be like a change from 0 to 50 in like a split second. Okay, so if you don't slow down, obviously you'll be thrown away from the center of the curve. Okay, because the force is pushing you away from the center of the curve. So the force will stay constant as you go, as you are negotiating, taking the band, and immediately when you get to the second tangent point, the force will be 0 again. So it's 0 to 50, 50 to 0. Okay, so the changes here is abrupt. We call it abrupt, very quickly. Okay, so we're going to try to avoid that. Okay, if we just have a circular curve, that's what's going to happen to us. Okay, that's what's going to happen when we taking the curve. All right, so we're going to try to overcome that. So what can we do? Okay, we can solve or alleviate the problem by, remember by definition when we say transition curve is a curve with different radii. So, okay, the radius changes, okay, from infinity to a certain value. Okay, let's look at this curve here. Okay, imagine that you're traveling from here, then that part there is your circular curve. Okay, so if instead of having a circular curve, we try to fit in a curve, a transition curve, which by definition we know the radius changes. So it's changed from infinity to r at this point there. Okay, so r could be, again, for argument's sake, let's say r is 600. So you could imagine there could be the radius will changes. Okay, so from a large value to a small value. So I'm just going to make things easier. Let's say over here it was 700, 800, 900, 1000, and infinity all the way there. So in terms of the forces acting on you, the force will increase gradually because the radius keep changing. So it will increase gradually from that point there, 0 on here, and you get to t, the radius changes but gradually. So it means that your p will also increase gradually, and will get maximum to that point when it's equal to little r is equal to big R. They will stay constant. Will stay constant along the circular curve till you get to the tangent point. Then as you go beyond that, the radius will increase and the centrifugal force will decrease gradually, and we get to there, it will be 0. So you can see that the change in the centrifugal force is gradual to its maximum value, then will decrease gradually to 0. So imagine that you're in the car, you're in the vehicle traveling, you can sense that, you know, your journey also, you will feel comfortable taking your ride in the car will be more comfortable taking the corner compared to taking the curve. Compare if it was just a circular curve. Okay, so when we talk about transition curve, we talk about the force. Okay, try to minimize the force. Okay, so when we put in two transition curve at the end of a circular curve like that, so in fact it's just like we could say that we're replacing a totally circular curve with a part circular, and at both ends will be transition curve. So we term that as a combined curve. So when I say a combined curve, so this is how it looks like. Okay, transition, circular, and transition. Okay, so the main reason why we introduce transition curve is basically to provide safety as well as comfort. Okay, right. So that's what we mean by transition curves. Okay, now apart from introducing transition curve to reduce the effect of centrifugal force, we also could further reduce centrifugal force by introducing what we call super elevation. Okay, what is it? Okay, super elevation in road construction is basically means we are elevating or raising the outer part of the curve. Okay, we're making the outer part of the curve a little higher than the inner part of the curve, which means that the outer part means away from the center of the curve. Okay, so by doing this, we could further reduce, or in some extreme cases, especially in racing, should I say, environment or situation, they try to, if they can, eliminate centrifugal force altogether. Okay, but for our day-to-day use, our normal highways, we will raise up the outer part of the curve so to further reduce the effect of centrifugal force. Okay, so by doing that, we can balance out the force to a certain point based on a certain speed. Okay, that is the reason why we have speed limits on the highway, because those have been installed, or those has been decided based on safety as well as comfort. Okay, let us see now. Okay, a simple figure there just to show. This is for illustration purposes, for me to explain. I mean, in real life, we wouldn't have a super elevation that looks like that, unless, of course, you're talking about maybe a racing situation. Okay, but normal day-to-day life is going to be, you won't find a road surface that looks like that. But anyway, just to explain how things are. Okay, that arrow there represents the centrifugal force. Okay, and that's our weight W, and N would be the resultant force. Okay, so if you try to balance out the force, okay, solving the forces, you will have F equal to that by taking into account the inclination, and since we try to make there's no force, so it's going to be 0. So by balancing the equation, we'll come up with this tangent alpha equal to V squared over GR, where V will be the velocity, R the radius of the circular curve, G of course the gravity, and alpha is the angle. So which means that alpha is equal to that. Okay, so now excuse me, I made a mistake there. Maximum super elevation is equal to that. Okay, so that value there, how do we get? By calculating that. The higher the speed, super elevation will be bigger. Okay, the same goes with the radius. Okay, smaller radius will be larger super elevation. Okay, that's a basic concept behind it. Okay, so when we remember super elevation is basically raising the outer part of the curve. So the center of the curve is that way. Center of curve. Okay. Now, this condition, this is super. The maximum will be when we hit the circular curve, if you remember. So along the circular curve is going to be maximum all the way. Okay. So from the straight, it's going to increase gradually till it get maximum to on the circular curve all the way. As soon as you leave the circular curve onto the transition, the next transition curve, the super elevation will reduce when it gets to 0. It will be 0 when you get to the last tangent point on the curve, on the combined curve. Okay, so a few pictures there just to show. I got it from the internet. A train, okay, taking a bend. You could see that the track at this part is a bit slanted. The outer part here is higher than the inner part. Center of the curve will be that way. Okay. And if you look at the engine is a bit tilted. Okay. But look at the coaches. Okay. That one is tilted too. But look at the one at the back, which is basically straight or vertical, should I say. So that means that's still the straight part of the track. So it gets to the circular or the transition curve. You could see that how the radius changes and how the super elevation changes. Okay, I think that's a good sort of picture just to explain super elevation. Next, we have this and the velodrome. I think you are aware of all this. Okay, when we watch the Olympics or World Championship on cycling and so on, is in a race condition. So that's why you could see the super elevation is so high or is quite tall in the sense that it's for racing purposes. In our day-to-day, as I say, day-to-day road, our normal highway we would not have something like this. It would be something like that. Okay, a bend, you could see. Okay, I think you can see with your naked eye that part there, middle of a circle, is not basically horizontal. It has a slope. Okay, so that if I try to imagine, that's a horizontal line. So that part there, the part where they raise the outer part, is called the super elevation. Okay, so how do we do that in real life? So I've got a little video here just to show. This is again I got from a slide share from the internet. I entered it into a video. Okay, right. Look at the green car. Okay, on the straight line now, and if I can just pause this. Okay, if I can just probably turn it back. There's something I got to tell you before we start. Okay, look at this cross section of the road. The cross section like that. Okay, so CL, the center line. Okay, and this diagram is a bit exaggerated, but I don't know whether you realize it or not. The center line of the road is always higher than the edges. Okay, simply because for water to flow when it rains into the side drain. On the roadside, there'll be side drain, so water could go in there. So it's only 2%. It's not that much. Okay, but still, that's the gradient. For this illustration, and they have drawn it quite a significant angle just to show, how the road surface changes. So CL, or sometimes this is also called the crown of the road. Okay, at the crown. Okay, so let's look now what happened. Okay, I'll probably just erase that to make things a bit clearer. Leave that one on though. Okay. Okay, as the car passes through the road, you could see the outer part here is going up. Okay, so when it hits the circular here, so you could see that it was maximum. Then when it leaves the circular part, it will reduce, okay, until it gets again to 2%, okay, which is the next rate. So that's how basically super elevation is applied or is introduced in road design. Okay, now don't want that. Next, okay, types of transition curve. Okay, basically four they are normally used in road design. So these are the most suitable curve that can be used, and the reason they're being suitable because they have this characteristic whereby the change of super elevation with respect to distance is at a constant rate. Okay, meaning that the change is gradually constant rate. Okay, till it gets to the maximum. So that's why we've chosen these four types of circular curve. So such circular curve is called a clotoid or a cubic spiral. Okay, so an interesting about this figure is that if, okay, imagine that that is your tangent to I, okay, and that will be your phi. Okay, at phi 30 degrees, all these curves, cubic spiral, cubic parabola, clotoid, and landscape, are practically the same curve, are practically the same up to that point there. Okay, so in majority of the cases, okay, where you're dealing with less than 30 degrees phi, the maximum phi, using these four types are basically the same. Okay, but however, when we dealing with railways, building up tracks, we don't use cubic spiral, clotoid, and landscape simply because the curve is too much. Okay, because trains cannot have sharp curve like that. So cubic parabola has a gentle curve. So that's why in railway design they normally use they basically use cubic parabola because it doesn't curve too great, okay, too much. But for highways, here we use cubic spiral, and that one here, okay, is what we call the landscape. Okay, it's used mainly at highways, entering or exiting highways. Okay. So cubic spiral or clotoid, okay, landscape for roads, and cubic parabola are basically for, not to say cannot be used for roads, it can, but mostly used in railway, okay, railway tracks. Okay, all right. Yeah, just another few picture snapshot from Google just to show you landscape, okay, applied in real life. That's if you're traveling from this end here. And let me change color. Prefer red. Okay, if you're from here, from this side, you're going to go to that side. You're going to take a turn off to the right. You'll take that curve down here, which probably just a transition curve, a simple clockwise. Then a straight here. So as soon as you get there, so you will be taking a lemniscate onto a straight line, then another transition, and another straight line there. So that's basically how we apply lemniscate and transition in road design. And there's another example for lemniscate used. Okay, this is what we call as a Cloverleaf Intersection. Okay, a combination there. Simple transition there, lemniscate. Okay, a few straights and another transition there, and so on. Okay. Right. Okay, so what are the equations? It's not as direct as a simple curve, okay, but we still have to look into it, because if you recollect, deflection angles are based on the geometry of the curve. We need to know what are the equations to represent angles, okay, so that we could calculate the deflection angle when doing the setting up. Okay, I'm not going to go into detail, but I just need the skeleton of it. Okay, the skeleton of it is you please refer to the recommended text if you need a full derivation of it. But simply, to put it simply now, for any cubic spiral or clotoid, okay, we know that the radius is inversely proportional to the length. Okay, width means that I'm going to put a constant in there. It's going to be 1 over r equals to ml. So if L is the distance along AB, so distance there, A to B, and if LP is the whole distance there to there, okay, let's call the LP, and that's basically the distance of the curve. And the curvature, okay, if you look here, if I have a point P, a point B, okay, if I draw a tangent there, okay, I'm going to call it phi. So phi is basically the inclination of that tangent against the main tangent to I. This is 2I. Okay, like I said, 2I. Okay, now I can draw another line there if I want and produce another tangent, so another phi. Okay, so at any one point on the curve, I can have a tangent and I can have a different phi. They say call that phi 1 and so on. So the curvature of the curve is given by the rate of change of phi with respect to L. Okay, that little one here, that's L. So, which means that d phi equal to ml times dl, and integrating will give you ml square, and so on. Substituting, you will get this, and finally, you get this for phi. Okay, and the other angle that we're interested in is the angle there. Okay, this angle there, delta. And delta, okay, basically it's got 1/3 phi, a third of phi, and put that in there, we'll end up with this. So L squared over 6R LP. So this is the two equation that we wouldn't be using often, okay, because they'll be the basis of our calculating our deflection angle. So that's basically what we want. Okay, when we do a setting up, we need the deflection angle as well as the distance. Okay, so that's for angles. How about distances? How about tangent lengths? Okay, Now, when it comes to the setting out itself, okay, before we get to the tangent length, let me get that slide first. Okay, let's look. Okay, BT2, which is that point there, BT2 is a tangent at T2, meaning that that's the end of the blue line is the transition curve. The red line is the circular curve. So is the end of transition, beginning of circular, and we call it as the common tangent point. Okay, because that tangent represents tangent for transition as well as tangent for circular. So CA, the distance CA, which is that distance there, okay, C to A, is a tangent at point A. Okay, whereas T1, T2, T3 are tangent point, and T1, T2 are tangent point for transition, and T2 and T3 would be the tangent points for the circular. So the length, that particular length, is given by the equation there. Okay, LP V cube over AR, and remember, V is in meter per second, and A is what we call the rate of change of radial acceleration, and it's in meter per second cube. Okay, a common, a standard figure that we use for A is 0.3. Okay, so if you're not given any value for A, then you can assume 0.3. It's safe to assume it's 0.3 if you don't have the information to do your calculation. So inclination angle, okay, when we get to that point there, phi max using the previous relationship will be LP over 2R radians. Inclination at phi will be L squared over 6R LP radians, and the deflection angle, as I mentioned earlier, was a third of phi. So the deflection angle at any point will be this one here, whereas for the maximum, which is at that point, deflection at point T2 will be 1/3 of phi, or LP over 6R. Okay, so that's basically as far as angles are concerned that you need to know. Okay, to calculate the deflection angle, and to check the deflection angle, we look at the relationship between phi and delta. Okay, that's for angle. How about for distances? Okay, so as I say, refer to the main textbook, the recommended textbook, if you need a full derivation of the equation. So first, there's a thing here we call a shift S. Okay, which is given by LP square over 24R. So the shift is simply means, imagine if that's a circular curve. Okay, imagine that's a circular curve. That's a two straight going up. Okay, let me just, okay, that's a straight T1 to I, and then from I to T2. Imagine that you're just going to put a circular curve. Okay, a simple circular curve. It's going to be something like that. Okay, since we're going to change that and make it into a combined curve, somehow we will put that transition at the end and the second transition at that end, that curve somehow has to go down in this case. So we call that a shift. So it's given by that number. Okay, then tangent length from there to there, okay, is given by that one there, which is self-explanatory, I think. Radius, the shift we just calculated, intersection angle, and the length of the transition curve. Then the length of the vertical curve, which is the distance, the curvature distance between T2 to T3, okay, is given by that, okay, if you're using radian anyway, okay, sorry, I got to change it to radian in degrees, from degrees to radian, so that's why we have that multiplication. So R theta minus 2 phi max, okay, and delta max, so this is delta max for circle, or for circular curve, is given by that, okay, delta max for circular curve, okay, is different from what we just discussed a moment ago, which is delta max for transition curve. So we're talking about delta max for circular curve is given by theta minus 2 phi max divided by 2. Okay, so that's some of the equation that you need to understand, not to memorize, because during exams, under examination condition, we will provide you with a sheet of paper of all the formula that you require. Okay, it's just a matter of knowing what is what. Okay, try to understand what the equation means.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.